Hello friends, welcome back to the next session of e-learning. My name is Vijay Sonar and I am from RC Patel Pharmacy College. In the previous session of NMR spectroscopy, we have been discussing about the how many different types of signals are possible in a given chemical compound, and we have seen the concept of chemical equivalence. In today's session, I will talk about the concept of chemical shift. What is the meaning of shielding and de-shielding? What is the meaning of upfield and downfield? And we will try to understand what are the different factors which affects the chemical shift. What is the effect of inductive effect? What is the effect of electron withdrawing group on the chemical shift? So let us continue with this next session. So what is a chemical shift? It's a shift of NMR signal with respect to TMS. It is represented by delta, and the formula is the observed chemical shifts in hertz divided by operating frequency in megahertz multiplied by 10 raised to 6. So this is the formula to calculate the chemical shift for any compound. These are on the x-axis the values written like 0, 1, 2, 3, 4 in ppm, that represents the chemical shifts. TMS, you can see the signal at 0 is the signal of TMS, that is tetramethylsilane, that is 4 methyl group attached to the central silicon atom. So it is the reference standards used in the recording of NMR because it has 12 equivalent protons. On the left side you can see a signal of methyl bromide. The difference between the signal of TMS methyl protons and the CH3Br methyl proton is because of the presence of electron withdrawing group. As we know, bromine is electron withdrawing group, so it will be on the downfield side. So on the left side it is called as de-shielded field or downfield, and on the right side towards 0 it is called as the upfield region or upfield zone. Now we will try to understand with the help of some suitable examples that what is the effect of the presence of electron withdrawing group. Let us consider these two examples, CH3Br versus CH3Cl. Now both of these compounds have one methyl group. Okay. Now let us talk about the electronegativity of the different atoms, different halogens. As we know that chlorine is more electronegative than bromine, so it means that because of the electronegative effect, electron withdrawing effect, the methyl protons of chlorine will be CH3Cl will be appear towards upfield. Now amongst the halogen, methyl fluoride, methyl chloride, methyl bromide and methyl iodide. So this will be the sequence of chemical shift. The protons of CH3F will be appeared at higher chemical shift values, while the chemical shifts of methyl iodide will be at downfield side. And this is the sequence CH3F. These are some of the values given in textbook. So you can find out the signal of CH3F at 4.3 ppm, CH3Cl at 3.1 ppm, methyl bromide at 2.7 ppm and methyl iodide at 2.2 ppm. If we compare all these values with the methane directly, so it will appear near about 1 ppm. These are the rough estimate values. So the summary is more is the electronegativity of the atom, more will be the de-shielding effect, and the chemical shift value will be appearing at upfield side on the towards left side of the NMR spectra. Now let us consider the another aspect. The presence of number of electron withdrawing group is another matter which will affect the chemical shift signal. Now let us consider this example. A compound with 3 chlorine substitutions, then the compound with 2 chlorine substitutions versus the compound with 1 chlorine substitution. So we are comparing trichloromethane versus dichloromethane versus monochloroethane versus simply methane. So as we have seen, more the number of electronegative groups, there will be more deshielding. So as we can see, this compound have 3 chloride groups, so this will have strong electron withdrawing effect on the carbon. So therefore this proton will be appear at about 7.3 ppm. It will be more deshielded, so the value will be more downfilled. Now the next aspect we have to say is what is the effect of position of proton with respect to the electron withdrawing group. Now this is 1 nitropropane. In this compound we can have three different types of signal. This is we can label as a signal A of methyl group. This is the signal B of second methyl group, and this is the signal C of CH3 group. Now as we have seen earlier, the electron withdrawing group have the deshielding effect. So now just try to figure out that among these 3 A, B and C, these 3 protons, which will be appearing at upfield and which will be appear at downfield region. So as we can see here, the CH3 protons, these CH3 protons are the far away from the nitro group, that is 2 carbon away. So it will be appearing at near about close to upfield side. So the methyl proton that is directly attached to nitro group, it will appear at more downfield side. So the proton of CH2 group labeled as A will be appear at 4.4, B at 2.1, and the methyl protons at 1.0, because it is far away from the nitro group, that is electron withdrawing group. So the effect of deshielding is very less for CH3 protons that is labeled as C, and the CH2 protons labeled as A, which is directly attached to nitro group, therefore it will be appearing at downfield side. Now let us consider the another aspect. This is another example. It's a ketone. Now in this compound we can have the 3 different types of signal: CH3 next to carbonyl group, CH2 next to carbonyl group, and methyl protons. So now among these we have to compare, or we have to find out which proton will appear at upfield and which will appear at downfield. Now this carbonyl group, as we know, is electron withdrawing group, so this will have a deshielding effect. And so now if you see the proton of methyl group labeled as C, which is far away from carbonyl group, so it will not have an impact of this electron withdrawing group. So CH3 will appear at upfield side. Now the battle is between the protons of CH2 and the protons of CH3, that is B labeled as A and B. Before we understand between these two protons, let us understand that the difference between tertiary, secondary and primary carbon. So let us consider the example of methane. This is the tertiary carbon, okay, because it is attached to 3 different carbons. This is the secondary carbon, which is attached to 2 different carbons, that is methyl. And so the proton of tertiary carbon will appear towards more downfield side as compared to secondary carbon, and the proton attached to a primary carbon will appear little upfield side as compared to secondary carbon. So we can see the methane protons will be more downfield than methylene proton, and methylene proton will be more downfield as compared to methyl proton. The rough estimate values are for methyl proton is about 0.9 to 1.1 ppm. For methylene proton, which has secondary carbon, is about 1.2 to 1.3 ppm, and for methyl that is 1.4 to 1.7 ppm. Now, what is the reason behind this? Why the proton at tertiary carbon are more downfilled than secondary carbon, which is again more downfilled than primary carbon? Again, the same reason of electronegativity. The carbon atom is more electronegative as compared to hydrogen atom. Okay, so you can see the tertiary carbon is attached to directly 3 carbon atoms. Okay, so the electronegativity value for proton is 2.1, and for the carbon it is 2.5. So as we can see in tertiary carbon, we have, this is tertiary carbon, we have 3 carbon atom attached, so it will have the more electron withdrawing effect on this proton. So therefore the proton at tertiary carbon will be more downfilled because it is attached to the 4 different carbons. On the contrary, if we compare the primary carbon, it has only 1 carbon attached. So we can now simply understand that the tertiary carbon will be appear at more than secondary than primary. Now let us look at this example again. So we have now the battle between methyl proton and a methylene proton. So the proton at A position, that is a methyl proton, is attached to only 1 carbon, so that it's a primary carbon. It is attached to a carbonyl carbon, and the methylene carbon is attached to 1 methyl group and a carbonyl group, so it's a secondary carbon. So just now we have seen that tertiary protons at tertiary carbon will appear towards downfield than secondary and then primary. Here we get our answer. So in this compound, if we compare, the proton at B position will appear towards more downfield side, then protons A and then proton C. So summary is tertiary, the proton at tertiary carbon will appear at more downfield side than secondary, followed by secondary carbon protons, followed by primary carbon proton. These are the rough estimate. For methyl group it is 2.14, for methylene group it is 2.45, and for CH3, as we have seen earlier, it is around 1 ppm. So methylene proton, because of it is attached to a secondary carbon, it will appear towards more downfield side. Now we will talk about some functional groups here. This is carboxylic acid. So the protons attached to these oxygen group, that is the protons of OH, will be appear at around 10 to 12 ppm, because it is directly attached to oxygen, which is a more electronegative atom, and the protons of aldehyde, they will appear at around 9 to 10 ppm. Now let us consider about the aromatic protons. This is the very important value to keep in mind. The aromatic protons, they will appear at around, this is the rough estimate, between 6.5 to 8.5. If an aromatic ring is attached with 1 methyl group, so this methyl protons, okay, they will not appear at 1, but they will be little down shielded, and the value is roughly 2.1 to 2.3. Now let us consider about the halogens. a proton attached to a carbon which is also attached to a halogen, as we have seen earlier, because of the electronegativity effect, it will be appear near about 2 to 4.5, and depending on the nature of halogen, whether it is fluorine, chlorine, bromine and iodine, the value will be de-shielded depending on the electronegativity of the halogen. Now let us consider this example. When you have a proton attached to a carbon which is having double bond, so it will appear near about 4.5 to 6.5 ppm, and for the proton which is attached to a carbon triple bond, it will appear near about 2.5 to 2 to 2.5. So these are the some of the rough estimate of the chemical shifts. So in this session we have seen the different chemical shifts, the meaning of chemical shifts, what is the meaning of upfield, what is the meaning of downfield. We have seen the effect of electron withdrawing group. We have seen the position of the protons with respect to the electron withdrawing group, that is 1 carbon, 2 carbon or 3 carbon away. Then we have seen the effect of different halogens on chemical shift. We have also discussed in this session the difference between tertiary, secondary and primary carbon and its effect on chemical shift. So in the next session we will discuss the another topic of the NMR interpretation. Thanks for the watching. If you have any questions on this topic, you can put me in comment box. Thank you very much for the watching.